All right, so the first part of the course is actually kind of a review of discrete mathematics. So if you took the class, discrete mathematics, and remember a little bit of sets and collections of elements, this is going to be a review for you. And if it's not a review, that's fine too. So we'll learn things here. So this is a review of sets. Yeah, most of you might know about these already. So let's recall what a set is. So a set is a collection. So I say it is a collection of objects. Now, those objects can be anything. So they could be numbers. So these are going to be what we call the elements also of the set. So elements. Those objects can be anything. Could be numbers, could be other sets, could be functions, could be whatever. So a couple of examples here. So let me just the white color here. So example. So one way to talk about sets is by putting them in a list. So usually sets are denoted by capital letters, for example, capital A, and curly braces is used for notation of sets. So a set could be, like, for example, 0, 1, and 2. This is a set. So it's a collection of the elements of the element 0, 1, and 2. So that is a set. And the elements are the things that appear inside this list. So another set could be, for example, B. It could also be combination, for example, A, 1/2, B, and C. So the elements here are, some of them are letters and one of them is a number. So this is also a set. Okay. Okay. Now sets are represented by this list with this curly braces. All right, so the sets are also represented visually. For example, if I want to represent my set A, we use a circle here and then just put the elements there, 0, 1, and 2. And this is what we call the Venn diagrams. And B is my other set, which is the element A, the element 1/2, the element B, and the element C. So all of this is what we call Venn diagrams. And we will use both of these notations here in the class. So what are the elements? So let's make here the elements of A. So the elements of A are, so let's look here at the elements of A. The elements of A are 0, 1, and 2. Those are the elements of A. So 0, 1, and 2. And 2. So those will be the elements of the set A. Now, if you are familiar, you remember discrete math, this is just a review for you. Now, let me introduce some notation here. So let's look at this notation. So notation. So this is going to be the notation. So given a set A, we write this notation X, and this notation here, this is like an E. This is the notation that says it's an element or it belongs to A. So the way you read this is X is an element of A or X belongs to A. So that if X is an element, it's an element of A. Okay. So let's look at the same set A, set A that we have here. So this one. Now I can write down this. I can write down that 1 is an element of A by just writing this notation. Okay, so it's saying that 1, the number 1, is an element of A. If you want to check that, the only thing you have to do is just look here at the list and check if it appears there exactly as that element, and it does, right? Now, when something is not an element, you cross that out. Now, this set A does not have the element 3 in it. So the number 3 is not an element of A. So we're going to cross that out to indicate that that's not an element of A. Okay. 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 So let me ask you a question here. So this is a question for you. So a question. Is this an element of the set A, which is 0, 1, and 2? Okay, okay, so this was a trick question. The answer is no. The element is this whole thing. This whole thing is the element. So the element is the set 1. So the set 1 does not appear there. The number 1 is there, but the set 1 is not there. Because when you say it's an element, it has to appear exactly, but this doesn't appear exactly there. So no. So what we're going to say here is that this is not an element. It does not appear in the list A. Okay. However, you can say that 1 is an element of A, and there is no contradiction here because these two statements are not the same. Okay. So I'm going to look at some important sets that we're going to see in this class. So important sets. So some important sets. So let's start with the natural numbers. So the natural numbers have this notation. It's like an N with a double bar at the beginning. And this natural numbers is this collection. So it's 1, starts at 1, and then 2, 3, and so on. Now, some books might have 0 as the natural number, but for us, natural numbers are going to start at 1. Okay. Now, if you read some other book in real analysis, maybe the book is going to say 0 is a natural number. For us in this class, it's not going to be. The reason for that is because the natural numbers, we're going to think about them as the numbers we use for counting. So this is numbers for counting. So there's numbers to use to count things. So 1, 2, 3, you start counting 1, 2, 3 usually. Now, if you're a computer science person, you start counting at 0. But for this is we start counting at 1. And whenever I use this notation, anytime during the class, what I refer to is this collection here. Okay. All right. So let's talk about some other set, the integers. Which is going to be a little bit different from the natural number. So the integers are going to have this notation. It's the letter set with that bar there. This is whole numbers. So 0 is going to be there. Plus or minus 1 is going to be there. Plus or minus 2 is going to be there, and so on. So this is going to be the collection of what we call the integers. So basically the integers are the natural numbers with all the opposite, which is -1, -2, -3, together with the number 0. So that's what we call the integers. Okay. Good. So let's look at the rational numbers. rational numbers. Now, the way that I express the set here, this is a list. So I'm telling you what numbers are here. Now, sometimes there is no way that you can give the list because you just need to write down the set as a description of how the elements look like. So what are the rational numbers? So these are all fractions of integers. Now that is of course in English, so we're not gonna think about it that way. We will have to think about it in a formal way, a more mathematical way. Now the notation for the integers is Q with this bar here. So that's gonna be notation for rational numbers. So these are gonna be basically the fractions. Now remember, these notations are gonna be important because I'm gonna use them throughout the course. So pay attention to those things. Now, I'm not going to give you a list. I'm going to give you a description. And this is what we call the set builder notation. The set builder notation is a way to describe a set without giving you the list, but giving you the properties that determine whether or not an element is there. So what are the set building notation? I'm going to write down A over B. So these are the type of elements. This vertical bar here means that on this side, I'm going to describe the property that these elements must have to be able to belong to the rationals. So they are fractions, but not all fractions. They will have to be fractions of integers. So in this case, A and B, they both need to be elements of the integers. And that's what this notation here means. Both A and B have to be in the integers. So this could be 0, plus or minus 1, plus or minus 2. Okay, let me ask you a question here. So this is the set building notation. These are the elements, and these are the properties that the elements must have. So the elements are these ones, fractions, and the elements A and B have to be in the integers. Now, in this definition, I am missing something. What am I missing here? Exactly. Very good. B cannot be 0. And why is that? Why B cannot be 0? So whenever you define this fraction, if you forget this, then you're allowing undefinitions here. So you have to be very precise. Now, this is not a list of elements. This is a description of the elements. This is what we call the set builder notation, which is a way to describe a set by looking at the properties that it has. So here, these are the elements of the set, and these are the properties that it must have to be able to belong to that set. Okay. Now you can try to give a list, but it's going to be very hard, for example, to give a list like, so you know, like for example, plus or minus 1 is a rational, right? It's a fraction of integers, and also, for example, plus or minus 1/3. But this, if you write it down in this way that I'm writing down right now, it's not very clear what the elements is. So someone might believe, okay, maybe the elements of Q have to have a 1 in the numerator, but that's not the case, right? So a better description is something like this, okay? All right, so let me ask you a question. So let's ask you this question. So the question here is this true? Is 4 an element of the rationals? Now, if it's an element of the rationals, let's go by the definition. So if 4 is an element of the rational, 4 must be able to be equal to a fraction, where A and B are integers and B is not equal to 0. So what fraction is 4? And that's enough, right? Because it's a fraction of integers. Okay. All right, let's talk about the real numbers. So real numbers, which is basically what we're going to talk about most of the time here in the class, the real numbers. Now, I'm going to give you a not such a formal definition in mathematics. And the reason for that is because I need to do some construction before that. So they correspond. So they correspond to points in the real line. Now, this kind of definition is not really a mathematical definition, but that's the best thing I can do for now. So they correspond to points in the real line. So what do I mean by that? So let's look at the real line here. So the real line extends on both ways. You have the 0 here, and let's say at the middle, and then you have 1, 2, and 3. So anything that can be identified with a point in this real line, we're going to call it a real number. So for example, let's say the square root of 2. Square root of 2 is somewhere over here. That's between 1 and 2. And then pi is somewhere over here, and so on. Now, why is this not a good definition? Because what I'm saying is this. What are real numbers? Real numbers they correspond to points in the real line. If you look at this definition, this is kind of a circular definition. So what are real numbers? Real numbers are real numbers. Right, so the definition for what set? For the real numbers or for... So the point is, it's not a very good definition because it relies on the picture. So one thing that let me give you another descriptive definition before we actually go into maybe a little bit of more detail on what the real numbers are. So the real numbers don't have holes. Okay, holes in the sense that, again, it's not very good. But looking at the picture, the real line doesn't have any holes in it. Okay. Now the notation for the real numbers, we're going to use it as an R with a bar there. So this is going to be the collection of all real numbers. And I'm going to go into a little bit of more detail about what holes are. So let me talk about that interpretation a little bit, because this is actually the main point. The main point of the real numbers is the real numbers is, again, not a very formal definition of real number, but the real numbers are a collection of numbers that do not have holes in them. We have to make that precise. And let me give you some idea on that. So let me give you an idea. So the sets that we saw already, the natural numbers, which is 1, 2, 3, 4, the integers, which is 0 plus or minus 1 plus or minus 2, and the rational is what we call discrete. Discrete in the sense that they will have holes in them. So if you look at some picture of the natural numbers, then if you start with 0, there is a hole between 0 and 1. I mean, 0 is not a natural number, so I'm going to erase that actually. So let me start with 1 and 2, 3 and 4. So you see here there are like right here in the middle, there are no natural numbers between 1 and 2, and there is like a space there. So it's discrete. Now the same happens with the integers, because if you think about it, in the integers you have 0 here, and then a little bit unit later you have a 1, and then you have a 2, and then on the other side you have -1, and then you have -2. So this set, which extends also on both sides, also has kind of holes in them. So this is discrete. Okay, so rationals. Now rationals also have holes in them. So it's really difficult to draw a rational, the rational line, because it's going to be all of them, the points are very close together. And I'm going to give you an idea why the rationals have holes in them. So let's say this is 0, and 1. And this is somewhere over here too. Now, this is all very dense here, but I will say that the rational numbers still have holes. Why is that? Because let's look at the square root of 2. Square root of 2 is here, right? Somewhere between 1 and 2, okay? Now, let me ask you a question. Is the number a square root of 2 a rational number? No, it's not a rational, right? So that means if this is the picture of the rationals, there is a hole at square root of 2. So that's the idea what I'm trying to say here. Even though the rational seems like really dense, like there is a rational right next to the other. For example, between 1/2 and 1/3, you can always find a rational in between. All right, so you can always do that. But the real numbers, they don't have any holes. So the real numbers are what we call a continuum. So the real numbers are a continuum. So which is basically a fancy way to say that they don't have holes in the sense of this picture, which we're gonna give an exact definition later, okay? Okay, the natural numbers, the integers, and the rational are discrete, and the real numbers are continuum. Okay, like time. You can think about it as time. So let's look at some notation here. So this is gonna be some notation for sets again. So if A and B are sets, so they are a collection of elements, this notation A with this symbol here, which is not the same notation as belongs to B, this is subset. So what that means is that the set A is a subset, so this is how you read it, a subset of the set B. And that means, so if A, then that indicates, so it's gonna indicate that let me clear that every element of A is also an element of B. Okay, so every time you take an element in the set A, that element is in the set B. Okay, I'm gonna give you the precise definition of subset. So this is the precise definition. So A is a subset of B with that notation if and only if this happens. And I'm gonna use this symbol here. And I will explain what all the symbols mean. For all elements X, if X is in A, then X is in B. Right, very good. So this is the actual definition of this. And this is what it says here in basic English. It means every element that is in A, that means or implies that element is in B, and that happens for every X. So for every X, that's the symbol. This is like a capital A upside down. You read it for every X. X in A implies, that's the arrow, X is in B. Okay. So you can also look at a picture, for example. So the usual way to look at something like this is think about both of those sets are living in some universal set. The set A is there, and the set B contains the set A. Or another way to say it is that all the A is inside the set B. So that will be the picture for that. Okay. Okay. So let's see some examples. So I'm gonna write down something, and you tell me if it is true or false. So let me write down some examples. One. Now, is that correct? So you can check that easily by saying, okay, I have a set here, right? That's what we call the set A, if you want to think about it that way. And this is going to be the set B. Right? Every element of the set A, let's say start with 1, that element of the set A appears also in the set B. Same happens with 2. 2 is in the set A, and it also appears in the set B. Okay. All right. So let's look at the second example. How about something like this? Is that true? This one here. Very good. So in this case, it's not true. So to indicate that it's not contained, we simply cross it out, right? So you say that this set here is not included in that set. Okay. Okay, let's see another example. How about that one? Is that true? So n is 1, 2, 3, 4, and so on. And the integers contains that because the integer, remember, is 0, plus or minus 1, plus or minus 2, and so on. About that one, is that one true? These are the integers, 0, plus or minus 1, plus or minus 2. All of them can be viewed as fractions. So that's what the rationals are, right? So one more. How about this? Is that true? No, that's not true. Why is this not true? Square root of 2 is here. It's a real number, but it's not there, right? It's not in irrational. Remember, the definition is every element here has to also be here. And in this case, a square root of 2, then it's not. Okay, so in that case, we indicate that by just crossing out that thing there, okay? So operations on sets. So we have to do some operations with sets. So we say A and B are sets. So we usually indicate sets with capital letters. So just A and B. So that's going to be 2 sets. The union of A and B is the collection. So as the collection of all elements that are either in A or B. So if it is at least in one of them, then it's true, is an element, or could be in both. Okay, could be in both. So the notation that we're gonna use for this operation, which we call the union of the sets, is gonna be this. So is A U for union B. So this A union B is the collection of all the elements that are either in A and B or both. Now the actual definition or the formal definition, mathematical definition for this is like this. I'm going to use set builder notation. These are all the elements X, vertical line to indicate such that X is in A or X is in B. That's the definition of the union, which corresponds to this part here in English. So it's the collection of all elements that are in A, B, or both. So X is in A or X is in B. Now, or here can also be true if both of them are. So X in A and X in B is also a possibility there. Okay, so let's look at the picture here. So what would be the picture of that if we gonna use pictures in a Venn diagram? So we have the universal set, and then we have, let's say, the set A is here. And usually what you do is you draw them so they have some kind of something in common. So the union is everything that is inside both A and B, and also that is also either here, or is common between them. So all the union will be this region here. So that would be the union of A and B. Okay. So let's see. Let's look at an example. Let's say the set A is the collection 1, 2, 3, and 5, and B is the collection, let's say, 2, 3, 6, and 1. So those are the two collections, two sets, A and B. Let's look at what the union will be. So what is the union of A and B? So the union is not difficult to find if you actually have the elements here. Now, it could be a little bit more complicated if you have other kinds of sets. So this is not really complicated, but let me ask you this question. What is the natural numbers union with the integers? What do we get? So if you take the natural numbers and you union with the integers, you get back. So that's the union. All right, so let's talk about the intersection. So let me scroll down a little bit here. So the intersection of the set A and B, this is going to be denoted by this symbol. So it's going to be A, an upside down U. So that's the symbol for intersection, and then the set B. So that's going to be intersection. Is, let's say that in English, and then I will say that precisely. So it's the collection of all common elements between A and B. So it's the common elements of both. So they have to be, for something to be in the intersection of A and B, it has to be in both at the same time. So let me give you the exact definition of this. So what is A intersection B? So I'm going to use the set builder notation. It's the collection of all the elements X, whatever those elements are, such that X is in A and, look at this and, X is in B. So the element X has to be in both X and B, A and B. See the main difference between this one and the union? For the union is with an OR. So if you look at the union, this should be instead of an and should be an or for the union. So the intersection is different. So let me give you the picture here. So the picture will be, so if you have the universal set U, then you have the set A is somewhere over here, and then you have the set B somewhere over here. Now it's going to be what they have in common. So what they have in common, it will be this area right here in the middle of both. So that's what they have in common. So it will be this part right there. Okay. So let's go back to, so let's look at this example here. So the example, I think these are the same sets we had before. Let's say A is 1, 2, 3, and 5. So that's the set A. And the set B, let's say, is the set 2, 3, 6, and 1. Now in this case, let's try to find the intersection. So A intersection B. Now they have to be, for an element to be in the intersection, remember that it has to be in both at the same time. Okay, is 1 in the intersection? So 1 is here in the set A, and is also in the set B. How about the number 2? How about 3? How about 5? All right, so that should be it, right? So that's the intersection of A and B. Okay. Okay, let me do something a little bit different. So I'm gonna give you 2 sets, and they're gonna be defined using the set builder notation. So A will be all the elements that are in the real numbers such that -1 is less than or equal to x and is less than or equal to 0. And my set B is going to be all elements that are in the real numbers so that x is bigger than or equal to 0 and is strictly less than 1. So basically what I'm saying here, if you look at the definition of this, these are basically intervals in the real line. Okay. Now the first set A here are all the numbers between -1 and 0, including -1 and 0. So if you were to draw this on the A on the real line, it will have 0 here, -1 here, and it will be a close interval. So it will be this. Okay, so that will be the set A. Is that making sense for everybody? And the set B, in this case, is all the real numbers, the set builder notation, that are bigger than or equal to 0 and is strictly less than 1. So let me draw it here. So that's going to be, let's say, 0 here and 1. So 0 is included, so I'm going to use the bracket, and 1 is not. So remember, you use the parentheses there. So it's going to be all these elements that are here. So those are basically the sets A and B. Okay. All right, let's look at what is the union and the intersections. So let's find A union B and A intersection B. I'm not going to ask for a proof of anything in this case, but let's try to see, at least graphically, what the solutions are. So let's look at the union. So the union is the elements that are either in A, B, or both. So what happens if you make the union of this set together with this set? Now let's look at the intersection. So the intersection is what they have in common. What do they have in common? So it's going to be the set that has only the element 0. So let me make a comment here. I think this is important to make. the set of only the element 0 is not the same as the number 0. Is that because one is a set, this one here is a set, and this is just a number, right? So saying that A intersection B is 0 is not correct, right? Because this should give me a set. Okay, yeah, you can also write it as a set. So both ways are fine. So in here, you can also say something like X in the real number. Yeah, so that will be actually more proper in that case, less than 1. So that would be a little bit better, more formal in that case. Yeah, very good. Now, the union of intersections do not have to be only with 2 sets. So you can take unions of 100 sets or 1,000 or arbitrary number of sets. So let's talk about that. Unions and intersections can be defined for more than 2 sets. So for example, if you have like a collection of sets, so A1, A2, let's say up to AN are sets. So you have a collection here of N sets, like say 100 or 1,000 or something like that. Then we can talk about the union of all of them. So we're going to indicate that by this A1 union A2 union, the 3 dots union AN. Okay, so it's going to have a similar meaning. This is the collection of all elements that are either in A1, A2, all the way up to AN, or they have in common. So one way to do it is, so everything notation would be the element X, so that X is in A1, or X is in A2, or all the way to X is in AN. So that will give us the definition of the arbitrary union. Okay. Okay, so I'm gonna give you a little bit more notation here. Instead of writing all this up on the left-hand side, you can use a notation which is similar to summation. So you write down a big U and you say I from 1 to N of A sub I. So basically is A1, I goes from 1 to N, so it's A1 union A2 union AN and so on. And a similar thing we can do for the intersection. So for the intersection, if you have A1 intersection A2 intersection all the way intersection to up to the AN, this is going to be the collection of all elements X that are in A1 and A2 and each one of them. So let me just write down this better. X is in A2 and X is in AN. And a similar notation we can use here, instead of writing down all of this on the right hand side, we write down a big symbol for intersection and we say from I equals 1 to N of A sub I. It's just a way to save a little bit of time, okay? You can actually extend this more. You don't have to stop at some point. You can have an infinite union and an infinite intersection. So you can have things like, for example, using this notation, the union from, let's say, I equals 1 to infinity of A sub I, and that's going to be A1 union A2 union, and so on. And this is it's not gonna stop ever. So there's gonna be a union of infinite number of sets. And then we can also have the intersection from I equals 1 to infinity of a sub I. So in this case, this infinity here means that you start at 1, 2, 3, and so on. You go all the way to infinity. And then this is going to be an intersection, A1 intersection, A2 intersection, all the way up to infinity. Okay. I'll see everybody then on Thursday. Take care of yourselves.